session of trigonometric lessons. This time we're going to cover section 5.4, which is about graphs of tangent, cotangent, secant, and cosecant functions. Last time we talked in detail about graphs of sine and cosine functions. Okay, as you can see, the first thing I have on the screen is the table of special trigonometric values that we've seen before, and I thought it would be a good idea for us to take a look at these before we began our discussion of the graphs of these other four basic trigonometric functions. So the reason I'm showing this is because each of these trigonometric functions, the tangent, the cotangent, the secant, and the cosecant, are a ratio of some kind, right? So they are a ratio of other trigonometric functions. The importance of that is that whenever you have a ratio, if the denominator of that ratio is 0, then the whole function is going to be undefined. So we need to be aware of those restrictions on the domain of each of these trigonometric functions, because as you remember, the sine and cosine functions do not have that issue because their domain is from negative infinity to infinity, but not these four functions. Whenever the denominator of the function that they're equivalent to is 0, we're going to have a vertical asymptote. For example, the tangent that you see here is equal to the tangent of any function. Let's say tangent of x is equal to sine of x divided by cosine of x. So for the tangent, whenever cosine of x is 0, you're going to have a disruption in the domain. You're going to have a gap in the domain because that's when it's undefined. So where do we have cosine of x equals 0? Well, from previous lessons, at pi over 2 or at 90 degrees, which would be this, at 90 degrees, the cosine of the function is 0. You see that? So in the denominator, we can't have 0. Therefore, at pi over 2, in the graph of tangent, at pi over 2, we're going to have a vertical asymptote. So where else we're going to have this issue for tangent? Well, notice that if I move this up, so for a tangent, that's the only place we're going to have of these special angles. At 90 degrees, tangent of a 90 degrees is going to be undefined. And that's just within these angles. But are there other values at which the tangent function is going to be undefined? Absolutely. There are infinitely many values. There is 3 pi over 2, 5 pi over 2, 7 pi over 2. All of these multiples of pi over 2, or odd multiples of pi over 2, you're going to have the tangent function undefined. The other function, the cotangent function that you see here, can be written as another ratio of other trigonometric functions. Cosine of x, so cotangent of x, can be written as cosine of x over sine of x. So what does this tell us? It tells us that whenever sine of x is equal to 0, the cotangent function is going to be undefined. So where among these special angles, at which point we're going to have sine of x be equal to 0? Well, at sine of angle equal to 0, the sine of 0 is going to be 0. So as you can see, at 0, sine of 0 is 0, so the cotangent, which is the function we have here, is going to be undefined. The secant function, as you recall from the previous lessons, is equal to 1 over cosine of x. So whenever the cosine of x, this is a ratio, right? So whenever the cosine of x is equal to 0, this whole function secant of x is going to be undefined. So where is cosine of x equal to 0? Well, we just mentioned at pi over 2, right? So here, pi over 2, that's 90 degrees. The cosine of 90 degrees is 0. Therefore, the secant at 90 degrees is undefined. Okay? These are very, very important for you to remember. The other, let's talk about the cosecant. The cosecant function can be written as, this is cosecant, CSC, cosecant of x can be written as 1 over sine of x. Okay, so because the cosecant is equal to this ratio, whenever the sine of x is equal to 0, we're going to have cosine of x become undefined. So at that point, where sine of x is equal to 0, we must have a vertical asymptote. So at which point sine of x is equal to 0? At 0. Sine of 0 is 0, and you can see that cosecant of x at 0 is undefined because of that relationship between cosecant and sine of x. Okay, so we can show this. We can show this in the computer as well. I think that would be nice for us to look at. So I'm going to switch from the dock camera to our computer so you can see some of these at play. So we have, let's do the tangent function. So tangent of x is has that kind of graph, right? So it has the range of, as you can see, these lines are going to go from negative infinity to infinity vertically, but you can see that there is an asymptote, right? So let me put in one of those asymptotes. So x equals, we know that tangent is sine of x over cosine of x. So wherever cosine of x is equal to 0, which would be at pi over 2, we should have a vertical asymptote. So let's put in pi over 2, and you're going to see where that asymptote is, pi over 2. Now that blue line, let me switch to the projector mode like that. So that blue line that you see right there, that's an asymptote. Vertical asymptote. Look at these tangent lines, tangent function lines that are getting very close to it. But if we could put a microscope and look at that, I can zoom out like this, and you can see that that asymptotic behavior continues, and for all of these tangent curves. Okay, so now you know why that tangent function exhibits that kind of behavior. Okay, so the same way, so we can also look at the cotangent function. So cotangent of x has this kind of graph. It's almost like the tangent function, not almost like, but exactly the tangent function flipped, right? So we know that if you take the inverse of the tangent function, you get the cotangent function. So and you can see that graphically. It's just the tangent functions flipped, going the other way around. I mean, I can put in the tangent function so you can compare them. like that. So the green ones, if I can zoom in, the green ones are tangent functions, and the red ones are cotangent. Look at that, the green ones, the tangent function, are increasing from left to right. But the cotangent function, which are the red lines, are decreasing from left to right. And the shape of the graphs are identical, but one is the flipped version of the other. Okay, and that's true symbolically. The two functions are inverses. One function, to obtain one function, you simply take one divided by the other one. You take the inverse of the other function and you find the other function. Okay, we can also look at we looked at the vertical asymptote for the tangent function, so why not do the same thing for the cotangent function? We know that cotangent function is cosine of x divided by sine of x. So wherever the sine of x, which is in the denominator, equal to 0, we're going to have a vertical asymptote for the cotangent function. So where do we have sine of x equal to 0? At x equals 0. So let me do that. So at y equals sine of 0. Well, let's see. No, that's not one I wanted. Let's see. So at let's put in sine of pi and see if that'll work. No, that's not. Oh, I see what the problem is. That should be x equals, not y, sine of x equals sine of 0. And you can see that right at that point, and I can zoom out, and you can see that clearly there is an asymptote right there. And there are infinitely many vertical asymptotes in the cotangent function, each of them where the sine of an angle is equal to 0. Okay, so, and which would be at 0, at pi, at 2 pi, 3 pi, 4 pi. At any multiple of pi, we're going to have a vertical asymptote where the cotangent function would be undefined. So I'm showing, before we see the formulas, I wanted you to see it graphically, and hopefully that'll help you make connection between these graphs and the formulas that we see. And of course we have the secant and the cosecant functions. So the secant function looks like this, right? So secant function is 1 over cosine of a function. That's the formula for a secant function. So wherever the cosine of x is equal to 0, which would be at pi over 2, 3 pi over 2, 5 pi over 2, and all of those, at those points we're going to have a vertical asymptote, which would be right there between, you see each pair of upper and lower curve. In between each pair there are vertical asymptotes. We can look at one of them. So x equals, let's say, pi over 2, right there. You can see that there is a, let me zoom out so you can see it better. Right there we have an asymptotic behavior, right? And we have infinitely many of these vertical asymptotes. So, and you might wonder, if you're curious, you're saying, why are they curving? Why are they curving like that? What's in between? Well, we know that this is, secant function is 1 over cosine of x function. So let me draw the cosine function. Those curves, the bottom and top of each curve is right where the cosine function is equal to either 1 or negative 1. Let me zoom in a little bit. That way, that's better. So right there, you have y equals cosine of x equals 1. Right here, you have cosine of x equals negative 1. So let me draw this so you can see it right there. Remember from last time, please, that sine and cosine functions, the basic ones, have an amplitude of 1 and negative 1. So the function swings up and down vertically between 1 and negative 1. That's true for sine of x. That's true for the basic cosine function. So that's where this one, when I put my cursor on it, it says 0, comma 1, right? When I put my cursor here, it says pi, comma, negative 1. Okay, so the red curve that you see is the cosine function, and the secant function, which is 1 over cosine function, has a minimum point at 1 to infinity. That's the range for it. The range of the secant function, you can see clearly. It's from 1 to infinity, union, right, from negative infinity to negative 1. You see, minus pi, comma, negative 1, pi, comma, negative 1. So this top point for the green curve, it's negative 1 here for the lower ones. And it's 1. This vertex it starts at y value 1 and goes up to positive infinity. And for here, it comes up from negative infinity up to negative 1. Okay, I hope this is helping you to get a visual understanding of how these functions are connected with each other through asymptotes, through high and low points like that, and so on. So we did the secant. Let's also take a look at the cosecant function. So the cosecant function looks like that, which is very similar to secant function, but the asymptotes are at a different place, right? The asymptotes are because cosecant function is equal to 1 over sine function. So wherever the sine function is equal to 0, this function would be undefined. So we're going to have a vertical asymptote wherever x equals 0, or sine of x equals 0. So let's put that in. We say x equals sine of, we can say pi or 0. I've said 0 before, so let me do pi. There. Sine of pi is equal to 0, and that creates this vertical line, which you can see is an asymptote. It would be a vertical line because it's x equals that, but the important thing to notice is that at sine of pi, you have a vertical asymptote for the cosecant function. Why? Because 1 over 0 is undefined. We can put in sine of 2 pi. Let me do that. X equals sine of 2 pi. Well, let me change that to 3 pi. Okay, it's still showing it right there. So any multiples of pi, it's going to be a any multiples of pi is going to be a vertical asymptote here for the cosecant function. Okay, so now we know why, right? All right, so let's switch back to the dock camera. The other thing I wanted to talk about is that sometimes you see expressions in the book or elsewhere on trigonometric functions that are redundant. So I wanted to talk about those so that when you see them, you notice that they are the same thing. There's no difference with them. So we know that the cosecant and secant functions are reciprocals of sine and cosine functions respectively. So the cosecant function is the reciprocal of the sine function, and the secant function is the reciprocal of cosine function. We know that. For that reason, the period is the same thing. So therefore, thus cosecant of x and secant of x have period 2 pi, which is the same as for sine and cosine. Okay, so what does this mean? So if you see expressions like that, like this, they are equivalent to each other. So cosine of x plus 2 pi, which is the period here, is equal to cosecant of x. So if we plot this and these two, you'll see the same curve. They are right on top of each other. You're not going to see two different curves. As a matter of fact, I'll go back to the computer to show you that. The same thing is true for secant of x plus 2 pi. This is equal to secant of x, because the period for secant of x is 2 pi. So if you write it like this, it's the same thing as if you write it like that. So let's go back to the computer here. So we can say cosecant of x, right, which is that. Notice if I type y equals cosecant of x plus 2 pi, it's the same thing. The black curves overlaid or were superimposed on top of the green ones. There is no difference between those two. The same thing is true for secant. So if I change this, secant of x, and change this, secant of x plus 2 pi, you see the same curve. There is no distinction, right? You don't see, both of them are being plotted right now, but you see just one set of curves for both of these functions. It's because they're the same function. Okay. I'm going to go back to tangent and cotangent, have the same, but for tangent and cotangent, the period is pi. So we can go back to the dock camera. Okay, so by this a different note for that. So note that tangent and cotangent functions have period pi. So therefore, if you have tangent of x plus pi, that's the same thing as you say tangent of x, right? Because this period pi, it makes no difference. This function has the same period as this. But that's why I say sometimes you might see this, the left-hand side, but that's the same thing as that. And also the cotangent function of x plus pi is equal to cotangent of x. They're the same thing. Let me box that here. So those two forms are equivalent. They're not different functions. Okay, like that. So let's go back to the computer and show these as well. So if I change this to tangent of x and change this to tangent of x plus pi, like that, you see one set of curves. You don't see both plotted, right? Differently plotted. It's the same setup, it's the same function, these two. So we can change this to cotangent of x. This is a reciprocal of that, right? So I like to make a correction because I don't think I used the right word. Earlier I said inverse, so it's the reciprocal. I meant to say reciprocal. So that's a correction on what I said earlier. Reciprocal was the right word, not inverse. Okay, cotangent of x plus pi is the same function as cotangent of x. And tangent and cotangent are reciprocals of each other, and cosecant and sine functions are reciprocals of each other, and secant and cosine functions are reciprocal functions of each other. All right, so let's continue with this. So this is the next thing I'm going to write down. This is something I mentioned as we were talking about this, but this is in more detail. So for your notes, we've talked about it on the computer, but now let's make sure that this is in your notes. So because tangent of x is equal to sine of x over cosine of x, and because cosine of pi over 2 is equal to 0, and cosine of negative pi over 2 is equal to 0, right? That the denominator is going to be 0 at these values, pi over 2, which is 90 degrees, and minus 90 degrees. Then the graph of function f of x equals tangent of x has vertical asymptotes, which we saw on the computer, right? At x equals pi over 2 and x equals negative pi over 2. And we should qualify this, all of this, that this is over the interval. Over the interval x greater than negative pi over 2 and less than pi over 2, right? So x cannot be equal to negative pi over 2 or pi over 2, because at those points the denominator of this function, the tangent function, is going to be 0. I can't emphasize enough that when you see tangent of x, in your mind you should remember this formula. This is critical for understanding this subject. It's critical for working with the formulas in this subject. Very, very important. So when you see tangent of x here, a function like that, you don't remember just what tangent of x is, but what connection it has with the other basic trigonometric functions. So we saw the graph of the tangent function on the computer. I want this to be also in your notes, so I'm going to draw it. And I'll get my straight edge one. All right. So here is the x-axis. And the y-axis here. And I want to call this f of x because in my notes I have, in the formulas you see this f of x. So instead of y, f of x. And we just saw that at pi over 2 and negative pi over 2, there's going to be vertical asymptotes. So this is going to be that. This dashed line is going to be that. So this is x equals pi over 2. And this one, x equals minus pi over 2. So the graph of the tangent function, as you know, it goes on. There are infinitely many replications of this, but we're looking at the graph of the tangent function in this interval between pi over 2 and negative pi over 2. It's going to look like this. Okay, like that. Okay, so let's add some notes to this. These are the things you should know or notice about the tangent function, is that graph of the tangent function is symmetric with respect to the origin. So how do we know that? If you fold this arm on top of, at origin on top of the other, it superimposes, this arm superimposes the other arm. So it's symmetric with respect to the origin. The domain of this, as you can see, it's going to have gaps, right? The domain of the tangent function is going to have gaps because of these vertical asymptotes. So let's write, and it's going to have infinitely many gaps. And we're going to write that down. Domain of that function is all real numbers except x equals pi over 2 plus n pi. Except these values, all real numbers, where n is an integer, like that. The other thing we should know, the range of this function is negative infinity to infinity, right? Which range is the behavior of this curve with respect to the y-axis. So the range, right, this was the domain. And now we have the range. It's going to be negative infinity to infinity. And the graph is clear, makes it clear why this is true. And finally, the tangent function is an odd function. So let's write that. F of x equals tangent of x is an odd function. What does this mean? Well, it means this. It means that tangent of negative minus x is equal to minus tangent of x. That's what this means. So this minus can come in front. So if the argument of the tangent function has a negative, that negative can come in front, and that's what it means to be an odd function. We learned this in pre-calculus 1, so this is where we make use of it. Okay, so let's look at, as you go through this video or these notes after when I post them on Canvas, please make sure you read these notes. Don't be surprised. If you read each page or you look at the video once and you catch everything, that's wonderful. But if it doesn't happen, that's quite normal. So please get used to the way to study this subject is maybe you'll have to look at these pages more than once. You might have to read them more than once or twice or 3 times. You might have to look at the video multiple times. But that's the nature of this subject. It's not you. It's that it takes a while for this stuff to sink in your head. And it just takes reviewing and reviewing multiple times. It's just the nature of this subject. Okay, we talked about the tangent function. So let's talk about the cotangent function. So because cotangent of x is equal to cosine of x divided by sine of x. So when I was saying earlier that when you see tangent of x, you should think of sine of x divided by cosine of x. The same applies here. When you see cotangent of x, you should think of it as cosine divided by sine. And because sine function, sine of 0 is 0, and sine of pi is equal to 0, then the graph of function f of x is equal to cotangent of x has vertical asymptotes at these points. This is important. At x equals 0 and x equals pi. Of course, this happens over that interval, right? From 0 to pi. Over the interval x between 0 and pi. Okay, let's draw the graph of the cotangent function. of course, at those points, we're going to have vertical asymptotes. So I want to draw, because x equals 0 would be the y-axis, right? So I'm going to use my thick marker to make dashed line right next to that. And that is x equals 0. And of course, x equals pi, right? So let's assume that's where the pi is. I'm going to put a dashed line right there. These are our vertical asymptotes, x equals pi. And here, we're going to have like that and like that. So again, the cotangent function is the reciprocal of the tangent function. And so you might say, well, what is that point? This is halfway between 0 and pi. So it has to be pi over 2, but you can also see it from the formula. Because at pi over 2, cosine of x, or the numerator of this fraction, is going to be 0. 0 divided by anything is going to be 0. So we have that. The cotangent function at pi over 2 is 0. Okay. Then let's give it some more description, just like we did for the tangent function. So notice here, I'm not writing cotangent function as a cosine divided by sine, but as soon as you see this, you should remember this in your head, this relationship, okay? This graph is symmetric with respect to the origin, with respect to the origin. And the domain of this function, of course, there's going to be gaps in the domain, right? At 0, pi, over this interval. So, but let's explain the domain for all values, not just over this interval. So the domain is all real numbers except x equals n times pi, n equals any integer, and this was the domain, and then range. This is equal to range, of course, is the behavior of the function with respect to the y-axis. As you can see, there is no gap. It flows very smoothly from negative infinity to infinity, or infinity to negative infinity, from left to right, right? Decreasing from positive infinity to negative infinity. So this is negative infinity to infinity. And what do you think about this being an odd or even function? Do you remember from last time when we defined, or the previous two lectures when we talked about odd and even functions. So the only even trigonometric functions are the cosine and secant. And those two are related, right? Secant is the reciprocal of the cosine function. Those are the only even functions. All the rest, sine, cosecant, and tangent and cotangent are odd functions. So we ask, what does this mean? It means this, that cotangent of minus x is equal to minus cotangent of x. Okay, let's talk about the cosecant function next. I started putting parentheses around x, or the argument of this function, because I don't want it to mix, or I don't want to confuse anyone with x being part of these letters. No, that's the function name we're using, and this is the argument. Right? So the denominator cosecant function is equivalent to this ratio. So whenever sine function is equal to 0, then this whole cosecant function is going to be undefined. So we're going to have vertical asymptotes at these points. Okay? And when I draw the graph, I'll establish a relationship between these two so you can see how it works. And we've seen it on the computer, but you'll see it on the paper as well. And so on. So this function has n pi. So here I said n pi, up there I said so on. So sine of 2 pi dot 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 and so on. Here I said dot 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 n pi. So n can be anything, right? 4 pi, 5 pi, negative n pi, any of those. Negative 10 pi, 100 pi, anything. So n is any integer. Let me say integer. So you saw this on the computer. It would be nice to also show it on the paper. f of x. And then we know that at 0, so that's once again the y-axis, right? X equals 0 is the y-axis. So once again, I'm going to use my straight edge to put dashed lines right next to the y-axis. And then let's do another vertical asymptote at pi and another vertical asymptote at 2 pi. So I'll just put this. Can I put asymptotes at an inch apart? Yes, so let's do that. Let's put another asymptote here and another asymptote here. Like that. So this would be x equals 0. This would be x equals pi. And next one would be x equals 2 pi. Like that. So we know that the cosecant function is the reciprocal of the sine function, right? Do you remember what sine function looked like from last time? I hope you remember. So if we put a 1 here and a negative 1 here, so that's y equals 1 and y equals negative 1. So the sine function would look like this. Like that. So then maybe I should use a green, I'll use a thick black marker here. So the cosecant function would basically come here, touch the top of the sine function, bounce back up, and go toward the asymptote, the vertical asymptote. The same thing will happen on this side, coming from the vertical asymptote, touch the top of the sine function, or the low point of the sine function in this case, and then bounce back toward the vertical asymptote. All right, so that's these bowl-shaped that come into two pieces are the cosecant function. I hope these graphs are beginning to make sense to you. For example, here we have the function, cosecant function, that is connected with the sine function in this form. And here we have a graph that shows the connection, right, between the two. So this is this red is the sine of x function, and this the black pieces, that one and that one. These are the cosecant of x graphs. The screen looks a little bit fuzzy. I could be wrong, but let me try to focus this. Okay, that's better. All right. Like that. All right. So let's talk about the domain range and how this graph is symmetric. This is an odd function, so we know it's going to be symmetric with respect to the origin, but we're going to write it down. symmetric with respect to the origin because it's an odd function. And then let's talk about the domain. Is all real numbers except multiples of pi, right? So all real numbers except, how do we say multiples of pi mathematically? Except x equals n pi. That's how we say it. Multiples of pi, where n is equal to any integer. And the range, you can see what the range is, right? The range is from 1 to positive infinity, union negative infinity to negative 1, right? Once again, the range is, you can write it as negative infinity to negative 1. That's that piece. Negative infinity to negative 1. And then 1 to infinity for this piece. And of course union, because those two are for the same function. So that was the domain. And then range is what we just said, which is negative infinity to negative 1 bracket union bracket 1 comma infinity. That's what we just said about the range. Negative infinity to 1. Negative infinity to negative 1, right? And then 1, bracket 1 to infinity. That is, of course, is an odd function. So once again we ask, what does this mean? It means that cosecant of negative x is equal to minus cosecant of x. So the minus in here can come in front. Okay, so which function is left? If you said secant function, you're absolutely correct. Let's look at that next. Again, once you see secant of x function from this point forward, try to remember it in this relationship, that secant function is the reciprocal of the cosine function, with cosine function in the denominator. So, and that cosine of pi over 2 is equal to 0, and that's important, right? Because this denominator cannot be 0. We need to know where that denominator is equal to 0. That's one of them. Pi over 2 or 90 degrees is one place where cosine of 90 degrees is 0. We don't want that here in this function. And also we can say that cosine of 3 pi over 2 equals 0 and so on. Right? So we must have vertical asymptotes wherever the cosine is 0. Those are two examples only, but there are infinitely many asymptotes at x equals pi over 2, 3 pi over 2, and so on. Okay, so let's draw the graph for the secant function. So pi over 2 and 3 pi over 2, let's use that as an example. I will put, so this is 0, so let's put pi over 2 somewhere about an inch away from it. Well, that would be, yeah, that we could do that, yeah. So let's put that here. Here, and then 3 pi over 2 there, because that's a longer distance. So we have pi over 2 like that, and we also have this vertical asymptote. So we have x equals pi over 2, which is that, and x equals 3 pi over 2, 90 degrees, 270 degrees, right? And then, so in the formula, I made a connection between secant and the cosine function. So I want to draw the cosine function here. Before drawing the secant function. So let's label this as 1, because the basic cosine function goes up and down between 1 and -1 as an amplitude. We talked a lot about amplitude last time. So here we have like that. On this side, we can bring this down too, so it's no big deal. So we can do this like that. So that's the cosine of x function. And then the secant function, of course, would be that. Can you guess where the other asymptote should be on this side? X equals negative pi over 2, right, on this side. And then here also, so we're going to have like that. Like that. And then, of course, we can have another piece here like that. Okay, so these pieces, these are the secant of x function, like that, and also this one on the bottom here. Okay, so now, like I said, you don't have to draw the cosine function, but I wanted you to see the connection between the cosine function graphically and the secant function. That's why I drew it. But the secant function are just these thicker lines in black that I've shown. Okay. So let's describe a little bit more about the secant function. Remember, secant and cosine functions are even. Okay, so this is symmetric with respect to the y-axis, which you can see, symmetric with respect to the y-axis. So the domain here is all real numbers except, of course, where we have gaps or vertical asymptotes, right? Pi over 2, 3 pi over 2, and so on. So we can show that except x equals pi over 2 plus n pi. And n, of course, is any integer. And range. Guys, this graph, I just noticed this. This graph at this point is not drawn accurately. This top of the cosine function should have been aligned with -1. This one is drawn correctly, but not this one. So let me, as much as I can, let me correct this. So this should have been, this line should have been curved. If we had, so this should have done this, like that, for the cosine. And this should do this. So the secant function on this side, when we talk about range, I just remembered that I should have drawn that correctly. So it dips, it comes from -infinity to -1, the range I'm talking about, -infinity to -1, and then 1 to positive infinity. This is I know this is a little bit messy, but it's better than what I had before because it showed that the range was -infinity to something like -1.5 maybe, which is not true. So the range should be from -infinity to -1. Okay, so let's write that down. So this will be negative infinity to negative 1 bracket union 1 to infinity. And of course, this is going to be an even function. And we say, what does this mean? It means if you have secant of negative x, that is simply equal to secant of x. The secant of a negative value in the argument is equal to the secant of the positive value. Okay, so that's what that means. So last time we talked quite a bit about the transformation of sine and cosine functions, right? So today we talked about tangent, cotangent, secant, cosecant, secant. So now we're going to talk about the transformation of these graphs that you saw. Okay, we're going to talk about that. A lot of what we talked about last time applies here as well, including the period, including the amplitude, including the phase shift. Remember how we calculated those values for sine and cosine? It's the same here for these four trigonometric functions. So this would be that. So first we'll talk about transformations of tangent and cotangent, and next we'll talk about transformation of cosecant and secant functions. And let me quickly add, where k is some value greater than 0, so these tangent and cotangent, they have, remember how the period was calculated? 2 pi over k. Amplitude is absolute value of A, right? A. And phase shift equals B. Remember that? That number B. So this is so important that I'd like to box this, all of this. So let's do an example. We want to graph this function y equals tangent of 2x. Okay, so earlier I asked you guys that whenever you see things like this, try to make a connection between this and the other two basic trigonometric functions, sine and cosine. So we know that this tangent of 2x is equal to sine of 2x divided by cosine of 2x, right? So wherever the cosine 2x is equal to 0, we must have vertical asymptote because we're graphing. So we need to know where these vertical asymptotes are. So we know that whenever cosine 2x is equal to 0, we must have a vertical asymptote. So that means that, so if cosine of 2x equals 0, then 2x must be equal to pi over 2, right? That whole thing has to be equal to pi over 2 because that's when we're going to have this denominator being equal to 0. So let's solve for x. X equals pi over 4. So at pi over 4 and any multiples of pi over 4, any pi plus that, we're going to have vertical asymptotes every 180 degrees plus that, or pi over 4 plus pi, and so on. Let's see. So, okay, so at pi over 4 minus pi over 4, and so on. Well, that would be at every pi over 4 and pi over 2. Is that correct? So yes. So so we're going to have, so asymptotes are at pi over 4 plus n times pi over 2. So would that make sense? That should make sense. So pi, and then where would the other one be? We'll just do, 2 pi, so let me verify this. So before I keep this, I want to generalize that, but before that, let me switch back to the computer. So we want to, so tangent of 2x if we begin here, then that would be pi over 2. That would be pi over 2. Or pi over 2 and then pi. So every pi. So the asymptotes must be every pi over 2. So that would make sense. So if we say x equals pi over 4, yep, that, and then x equals pi over 2, No, that wouldn't, that would be pi over 4 plus, that's not correct, so pi over 4, so I want to say pi over 4 plus pi over 2. Yes, that's correct. So, and I'll just add to that. I just want to make sure. Yeah, that's correct. Okay, so let's go back to the dock camera. So this formula is correct. We're going to have asymptotes for this function. Asymptotes will be at these intervals. So if n is 0, then asymptote is going to be at pi over 4. If n is equal to minus 1, then we're going to have asymptote at negative pi over 4, and so on. So let's draw the graph. I'll do an asymptote at pi over 4. I'll do one pi over 4 plus pi over 2, which is 3 pi over 4. Right? So this would be x equals pi over 4. This one would be x equals pi over 2 plus pi over 4, which would be 3 pi over 4. So the point is, at whatever cosine of 2x, whatever this argument is pi over 2 or any multiples of pi over 2, we'll have an asymptote. That's how we're figuring these things up, or figuring them out. And then on this side, I'm going to put some asymptotes, negative pi over 4 and negative 3 pi over 4. That way we have the graph nicely shown on both sides. Like that. And also here, so this would be x equals negative pi over 4, negative 3 pi over 4. Okay, so then the graph of the tangent function is going to look like this, like that. This point of intersection is where tangent of 2x is equal to 0, which is at minus pi over 2. And then here, we're going to have another point of intersection, or x-intercept actually. So this will be x equals pi over 2. Okay, so let's do another example with the tangent function. We want to graph that function. So the amplitude is clearly 1, right? The, let's see. Okay, and the k in this case is equal to 2. So k is equal to 2. Therefore, the period would be equal to 2 pi over k. We learned this last time, right? 2 pi over 2, or pi. So the period for this, let's see, 2 pi, let's see, this period, 2 pi, I might have to, guys, I might have to do a correction to my previous notes. Let me look back. I'm talking about this page. Yes, I have to do a correction to this page. I'm glad I noticed it here. Yes. So the sine and cosine have period pi over k. I apologize for this. So let me correct this page 6. For sine and cosine, the period is 2 pi over k, but not for tangent and cotangent functions. I need to correct that. So this has to be pi over k. So pi over k. So that's the correction, pi over k, for both tangent and cotangent. So with that, then, did we need to do that here? We didn't do that here, but okay, so I might have to actually, yes, so that's why we need to, this example didn't do that, so I need to add something to this. So period here. Okay, so let me add, before we go to this page, so the period for this one, I should have done this for this example. I didn't, so let me put that in red here. So this would be, we need to factor this out. So you can write, well, you can write it like that if you want, or y equals tangent of 2 times x, and then k is equal to 2. So period is equal to pi over k, which is pi over 2. So for this case, the period is pi over 2, and so now you have it in for this example as well. So for tangent and cotangent function, period is pi over k, not 2 pi over k. So this is a correction to my notes to that as well. And this, in this example, then let me make the correction. So the period has to be pi over k. So this would be pi over 2, which is k in this case is equal to 2, right? K equals to 2. So the period would be pi over 2, and we don't need this one anymore. So that's the period for this function. And then, so this is now correct. And then, so what else do we need? Here we need to note the phase shift. Let's do a phase shift for this one. That's simply pi over 4, right? So phase shift equals B equals pi over 4. And so this would be, so interval for this would be pi over 4, comma, pi over 4 plus the period, right, from the last class, which is pi over 2. So this would be pi over 4, comma, common denominator is 4. 1, 2, 3 pi over 4. Okay. All right, so let's do that. Let's graph the this particular function. So between these two numbers, pi over 4 and 3 pi over 4, the function repeats itself, and you're going to see this in the graph. All right, so okay, so what do we have? We have pi over 4. Let's put that, so we're going to have let's put that here, pi over 4, and let's say, so the next one would be 3 pi over 4. That's the interval over which this is going to repeat itself. So pi over 4 to 3 pi over 4. Like that. And so let's see. So if we have, so the question is, where would the asymptotes be, right, in this here? So these are not the asymptotes. These are the x-intercepts. And let's see. So for the asymptotes, we must have 2 times. We might have. So tangent is equal to sine over cosine. So this thing cannot be equal to pi over 2. So that means this thing cannot be, if this thing, so let's find where the asymptotes are. So this whole thing, this whole thing, 2 times x minus pi over 4 cannot be equal to pi over 2, because that would be cosine of pi over 2, sine, because tangent is equal to sine over cosine, and at that point cosine would be 0, which we can't have. So if that's the case, that means this x, so let's see how we can solve for that. So we have x minus, we're solving for that, we're solving for x using this equation. So x x minus pi over 4, divide both sides by 2 to get rid of this 2, we will get pi over 4, and then x would be equal to, move this to the other side, pi over 4 plus pi over 4, and x is going to be equal to pi over 2. So at x values pi equal to pi over 2 and pi minus pi over 2 and pi minus pi, we should have vertical asymptotes. Okay, so let's do that. Well, if this is pi over 4, and so this is has to be pi over 2. Let me move this up a little bit. So this is pi over 2, x equals pi over 2. And then on this side, we should have minus pi over 2. So and at every pi over 2 intervals, we're going to have another vertical asymptote, right? So the next one over will be x equals pi, because that would x equals pi would be pi over 2 plus pi over 2. So let's put that in. And I'll put x equals minus pi on this side, right? That way we'll have the graph of this function on both sides. So x equals minus pi. Okay, so now we can draw these graphs for the tangent function. Like that. Another one for this. So the point of intersection on this side would be minus pi over 4. And on this side was 3 pi over 4, or so we're going to have minus 3 pi over 4. Like that. Okay, so that's that way. So I want to just do a recap on this. I'm glad we went over this example. One thing is, please note that the tangent and cotangent have period pi over k. And then also the asymptotes are determined by making sure that that piece, this piece, is never equal to pi over 2. Because let me write down here, you know that the basic tangent function is equal to sine of that function over cosine function, right? We know that. So the cosine is going to be 0 at pi over 2. So we need to make sure that that whole thing, which would be the argument of the tangent function here, that whole thing is never equal to pi over 2. That's what I did here. Why do I need to do this? Because I need to figure out where the asymptotes are. And the asymptotes are at every pi over 2 from the origin. So that's what we figured out here. And we use the phase shift to figure out the interval over which the function that we have goes through one full cycle or one full period, and that's that interval. So if you look at this graph, notice this interval, which is the interval over which the graph of the function goes through one full cycle, and then compare that with this graph, right? So we have these two together give us one full period. These two, going from here, so here and then here, it's going to be one full period. So here and then here would be one period. Okay, so we didn't have to show this on the other side, but it's nice because we have on the positive side we have some graph, and on the left side I thought we should give it we should draw the graph on the negative side as well. So that's why this is so important. I want to repeat again, the tangent and cotangent functions have period pi over k. In this case, k was 2. That's the number always in front of the parentheses, right there, between the tangent and the argument. That number is k. So that was the period. And the phase shift is pi over 4 from the formula, right? The formula that we have. B represents the phase shift. K is that number. And then we use the phase shift and the period to figure out where one full cycle happens, one full period happens. It happens between pi over 4 and pi over 4 plus pi over 2, which is the period of this function. And which is, when you add that, you get 3 pi over 4. So in this interval, we're going to have one full period. And then we figure the asymptotes, remembering that tangent of x equals sine over cosine of x. Cosine of x is going to be 0 at pi over 2. So we can never have this piece be equal to pi over 2. And that's what I did here. And that gave us that we solve for x equal pi over 2. So that's why you see the vertical asymptotes are drawn at every pi over 2 interval from the origin. So pi over 2, pi on this side, negative pi over 2, negative pi. And then we simply drew the graph. Okay, so now let's look at an example using the cotangent function. So we want to graph this function. Okay, the first thing we need to do is factor out the x. Remember, we need to do that in order to find out what is the phase shift and all of that, and what is k. So first thing, let's factor this out. We have y equals cotangent of 3 should be factored out. On the inside, we're going to have x minus pi over 6, right? Once you factor out 3. So if you distribute the 3 into this, you should get this original expression back. So now we can talk about k and phase shift. So k is equal to 3. Therefore, the period is going to be equal to, for the cotangent function, it's going to be pi over k, which is equal to pi over 3. So that's our period here. Then for the phase shift, that is equal to b, and b is equal to pi over 2, right? Because this is negative. If it was positive, then b would be minus pi over 2. But this is minus pi over 2, so b must have been positive pi over 2. Okay, so over which interval does this function repeat itself? We have the phase shift, which is pi over 2, comma, pi over 2 plus the period, which is pi over 3, right? So pi over 2, take the common denominator, we get 6, and then 3 pi, so it's 5 pi over 6. So over this interval, this function goes through one full cycle. Let's see. Period 5. This period. This is correct with shift. Oh, sorry. So let me correct. I was just looking at that. The phase shift is pi over 6. So this is what the function, after we factor out the 3, this is the function we're dealing with. So phase shift is pi over 6, not pi over 2. Let me correct that. And this, of course, will be pi over 6. So we have, this will be pi over 6. That's the phase shift, comma, the pi over 6 plus the period, which is pi over 3. Okay, now that's correct, and now I need to modify this as well. And so this will be pi over 6, comma, the common denominator is 6 pi plus 3 pi, so that'll be pi over 2. Okay, so I want to clean this up, guys. So let me, so this will be, so we want to graph. I didn't want to leave it like that. So graph this function. And so after we factor, we have cotangent of 3 times x minus pi over 6. So this is the function from which we want to draw the k value and the phase shift. So from this, we have k equals 3. Therefore, the period would be equal to pi over k, which would be pi over 3. That's the period. Now the phase shift would be equal to pi over 6, which is equal to b, right? From the formula that we learned in the lecture for section 5.3, and then also today we modified that same formula for the tangent and cotangent functions. So now the interval over which the graph of this function repeats itself or goes through one full cycle, it's going to be this. So let me write this down. 1 period is as follows. We have B plus the period, right? That's the formula. So let's put that in where what we have for this function. B in this case is pi over 6, comma, B again, pi over 6 plus period, which is pi over 3. So that's what all those numbers are coming from. Let's simplify this, and we get pi over 6, comma, taking the common denominator, we have 3 pi over 6, which is pi over 2. Okay, so over this interval, the function we have, this function, goes through one full cycle. All right, so let's figure out where this asymptote is. That we need to also figure that out. So asymptotes. First of all, you know that the cotangent function is equal to, or cotangent of x is equal to cosine of x over sine of x. So wherever sine of x equals 0, we're going to have an asymptote, right? But where is sine of x equals 0? That first thing that I talked about, and let me bring back that slide. When we began the lecture today, I brought this up, right? Where is sine of an angle is equal to 0? It is at 0 degrees, sine of 0 is 0. So we need to make sure that this whole thing, this is the factored form of that. We need the factored form to know what the k and the phase shift are. But to determine where the asymptotes are, where the vertical asymptotes are, we can use either this or that. So we need to make sure that this quantity is never equal to 0. So let's figure that out. We have 3x minus pi over 2 equals 0. We're solving for x to see what value of x would make this quantity equal to 0, right? We can't have that. And that would become our vertical asymptote. So 3x equals pi over 2. This is basic algebra. And then, so x equals pi over 6. So it is clear that at pi over 6 and then pi over 2, in this case, we're going to have vertical asymptotes. So let's draw. We have all the information we need. Let's draw our graph. I think I might be able to fit it here. Okay, so that's where the asymptotes are going to be, pi over 6. Let me mark off. The nice thing about figuring out the period is that the period moves everything by the same increment, right? The x-intercept moves by that same value. The asymptotes move by the same value. So that's why we need to find the period for each of these functions. It makes graphing much easier. All right, so we have pi pi over 6. I'm going to set my first so here, so this is x equals pi over 6. So pi over 6 plus. So, right, the period is pi over 3. That period moves everything with pi over 3 increments. So the next asymptote is going to be at pi over 3 plus pi over 6. We'll figure out what that number is, right? So let me draw this first. So let's figure out what this should be. So the next, this is, so asymptote is at pi over 6. And then, so x equals pi over 6 plus pi over 3. That's the period. This is the first vertical asymptote that which we figured out here. But the asymptotes are, the vertical asymptotes are moving according to the period, just like everything else, like the x-intercept, like every line on that curve, on the cotangent curve, it's going to move with the same period from one line to the next line. So let's figure out what this is. This is 6 is the common denominator, pi plus 2 pi. So that's 3 pi over 6 or pi over 2. So the next line is going to be x equals pi over 2. I think that's enough on this side. So let's put a couple of vertical asymptotes on this side, which would be minus pi over 6 and minus pi over 2. And then minus pi over 2. Okay. So between these asymptotes, we're going to have the curves. So for cotangent, the lines are decreasing from left to right. Remember that? So we can do one that goes here, goes through the origin, and comes back down here, like that. These intervals, guys, should be more equal, and the way I've drawn this is not, but they should be. And so here, so everything moves with this period. So if you have the x-intercept here at 0, this one, it's going to be minus pi over 3, minus the period. Everything on the graph moves with the period, with the same increment. So this would be minus pi over 3, which means this one, it's going to be pi over 3 plus 0. Pi over 3 is the period. So like that. Like this. And of course, this is pi over 3. Okay, so that's the graph of that function. Maybe we should do a recap, because this was with these lengthy examples, it would be good to do a recap of some sort. So let's do that. We began with this function, then we had to factor the inside of this argument because we don't know what k was. After factoring, we have 3 out. Inside is x minus pi over 6. So if you redistribute the 3 into this, you're going to get this expression back. That's how we determine if our factorization was correct. So this value now tells us in the factored form, we know what k is, k equals 3, and we know what phase shift is, which is pi over 6. So I use the k value to calculate the period. The period, I don't think I've mentioned this before, but the period is very important because everything on the graph, including the asymptotes, move with the same increment. So if the period is pi over 3, that means the asymptotes move with increments of pi over 3. If you have an x-intercept, it moves with increments of pi over 3 from x-intercept to the next one to the next one. Every point on the graph moves to the right or left with the same increment as equal to the period. That's very important to remember. So after noting the phase shift and the period, we determined the interval over which that function, that original function, goes through one full period or one full cycle. And after that, we had to figure out the asymptotes. So this is a cotangent function, which means at its basic form, it's equal to cosine over sine. Because of, if you remember that, then you know wherever the sine function is 0, you're going to have a vertical asymptote. Then I went and looked back at my special values table. Sine of 0 degrees or 0 radians is 0. So that'll be our the value which we don't want. So this whole thing cannot be 0 because at that point the denominator is going to be 0 and this whole function will be undefined. That's why. So using that 3x minus pi over 2 cannot be equal to 0. We solve for the asymptote. 3x minus pi over 2 equals 0. Solve for x equals pi over 6. And you can see x equals pi over 6. I drew the asymptote line, and then I was saying earlier that period, everything moves with increments equal to period pi over 3. So the next asymptote over, it's going to be pi over 6 plus pi over 3, which is pi over 2 after you do the algebra to it. You get x equals pi over 2. On this side, we get x equals minus pi over 6 and x equals minus pi over 2 are the vertical asymptotes. And of course, the point of intersection for this here, it goes from between these two asymptotes, the curve decreases from left to right, goes through the origin. Because everything on the graph moves with increments equal to the period, so you know the next x-intercept has to be at 0 plus pi over 3. So that's how I marked that. And the next one over, if we drew that one, that would be pi over 3 plus pi over 3, which would be 2 pi over 3. It would be the next intercept, and so on. Okay? And the only thing, to be honest with you, the only thing I don't like about my graph is that this distance from here to here between the asymptotes should be equal, and it's not. And I apologize. It was drawn manually, and so I didn't draw these equal to each other. But if we do this on a computer, those asymptotes are, so this interval, the distance between the dashed lines are equal to each other. So let me just leave it at that. And if you have questions about any of this, please post them on the discussion board where I'll be posting these videos. Okay, let's look at, so we looked at examples of tangent and cotangent. Let's look at transformation of cosecant and secant, and we'll do a couple of examples maybe on cosecant. Okay, so these formulas are very much like the other transformation formulas, but they are modified for the cosecant and secant. With k greater than 0. K should be greater than 0. These two functions have period 2 pi over k. So we're back to the period for sine and cosine. Remember, so the sine and cosine have period 2 pi over k. So do cosecant and secant. But tangent and cotangent have period pi over k. And of course, I should not forget to write down the phase shift as well. So in this formula, then let me write down that B is equal to phase shift. And this is so important, so I'm going to draw a box around this. Okay, so let's do example. Last time I did an example right underneath this and I ran out of space, so I don't want to end up doing that. So I'm going to move to a new page. So we want to graph one half x. And okay, so we need to know where the asymptotes are. We need to know the period of this, which means if you want to know where the asymptotes and all of that, we need to know where the phase shift is and all of that. So let's figure that out. So for the period, we know that for cosecant and secant, we're back to what it was for sine and cosine, which shouldn't be surprising because cosecant and secant are reciprocals of sine and cosine. So they'll have the same period, so which is 2 pi over k. In this case, k would be 1 over 2. So 2, and then doing the algebra on this, we have period 4 pi. Okay, so the phase shift here, B is equal to 0, right? So phase shift equals B equals 0. There is no B, which means B is 0, so it starts at 0. And so we can use this. So where are the asymptotes? Let's figure that out. So I'll just write it here. Of course, I have not been saying vertical asymptotes, but it goes without saying that we're talking about vertical asymptotes given what you saw earlier when I showed you on the computer. So this is vertical asymptote we're looking for. So we know that the basic cosecant function is equal to 1 over sine of x, right? So wherever sine of x is equal to 0, we know we're going to have a vertical asymptote and any multiples of that. So we have sine of 0 is 0 according to this, right? Notice that when at 0 degrees, sine of 0 is 0, and guess what? Cosecant of t or cosecant of 0 is undefined. Okay, so at x, if x is 0, we have undefined cosecant function. If x equals pi, we have undefined cosecant function. 2 pi, the same thing, so on and so forth, right? So then x cannot be, we cannot have, in this case, we want to make sure that half x is never equal to 0, right? So 1/2 x, that argument, let's solve for x using that, because so x equals 0, so this is our vertical asymptote at that point. And of course at pi, 2 pi and 4 pi and so on. So according to the phase shift and the period, so we have b comma b plus 2 pi over k. This interval, we talked about this formula in section 5.3. So please refer to those lecture notes on that if you don't if you're wondering where this is coming from. It's coming from that previous lecture. So this interval tells us from where to where this function goes through one full period or one full cycle. So let's figure that out. So b is 0, then 0 plus 2 pi over k, which is 4 pi. So 0 plus 4 pi. Therefore, the function goes through one full cycle from 0 to 4 pi. Okay, and here are the asymptotes, and other asymptotes are going to be at x within this interval, right? Within this interval, where are the other asymptotes? They are at 2 pi and they should be at 2 pi, yes, and 4 pi, like that. Will we have at pi, would we have an asymptote? No, because if you plug in for x with pi, you get cosecant of pi over 2 and sine 1 over sine pi over 2 that's just pi over 2 is just sine of pi over 2 is not 0, it's 1, right? So there is no asymptote at pi. It's at 2 pi and 4 pi and at 0. Okay, so all of this, we can then draw the graph. Because I'm going to draw my graph from 0 to 2 pi to 4 pi, so I'm going to give most of this blank space to the positive side, like that. This time I'm going to remember to put my asymptotes at equal distances, right? Otherwise, it won't look right, even though the numbers are correct, but the graph won't look right. So this has to be, so the first, well, let me do that with, so the first asymptote is at x equals 0, right? At x equals 0, let me put dashed line there. I'll try to put these dashed lines as close as I can to the y-axis, so that's x equals 0 as an asymptote, or the y-axis. Then this one would be at the 2 pi, roughly equal, right? Much better than my graph for the previous example. This looks a lot better. And also, so this is x equals 4 pi. Okay, so now we know that the sine function goes, the basic sine function goes from 1 to -1. So my lines for the cosecant function should curve around that and go up. Remember when I showed you with the computer at the beginning of this video? If you have doubts about it, please go back and look. You saw it on the computer screen that the curves that belong to cosecant and secant function, they touch the top and low points of the sine and cosine function respectively. So for cosecant, this line should come down here and then curve back up like that. So right there is the top of the sine function. If you want, we can do something like that. I don't want to draw too many lines because manually I might not draw things to where they should go, but like that. So I roughly sketched that one in. So the line that I drew is the sine function, and so the cosecant function is that, and the other piece of the cosecant function comes here and then touches the top of that sine function and curves back down like that again, and that top should be at -1, and that top and bottom should be at 1. Okay, so that's the graph of that. Let's do one more example. Okay, so now we want to graph this function. The first thing that should catch your attention is that the inside of the parentheses, the coefficient of the x, is not +1, right? It's pi. So we need to factor this expression on the inside so that the x has just coefficient +1. Otherwise, we won't know what the phase shift is. We need the k. When we factor this, we're going to know the k, which we can use to calculate the period and all of that. So the first thing we want to do is factor this expression, this argument of this function. Okay, so let's do that. And let me write this down so you have it in the notes. To know what k and b are. Of course, b is the phase shift, right? B r. Okay, so let's do that. We have y, 2 cosecant of, factor the pi out, we end up with x minus, of course, 1/3. So you redistribute the pi inside the parentheses, you're going to get this expression back. Okay, so now we can go ahead and list and find anything we need to graph this function. Now, this is the factored form. So let's start with the easiest piece of it, which is the amplitude, which is the absolute value of the coefficient of this function. So in this case, it's just 2 again. Right? So that's the amplitude. Then we need to find k from this, because then we're going to calculate the period. So k is pi, of course, right there. K is equal to pi. And from that, we can calculate period. Of course, cosecant function is the reciprocal of the sine function, and we know the sine function has period 2 pi over k when we have a phase shift like that, of course. Okay, so or we have some number other than 1 here. Otherwise, sine and cosine have period 2 pi, but with k, the period would be 2 pi over that k, whatever that number is. So cosecant is closely related to sine function, so the period is the same thing, which would be 2 pi. Here's the formula, 2 pi over k, right? So we have 2 pi over pi in this case, right? So then pi's cancel out. We get the period of that function is just 2. Okay. Now let's find the phase shift. which is of course easily found once we factor the inside. So it's just B, or the phase shift, is equal to positive 1/3. Okay, so together the period and the phase shift tell us over which interval this function is going to go through one full cycle, right? And the formula for that is this. So the interval over which the function will complete or completes one full cycle is, it has this formula, we've used it before, so it is B comma phase shift plus the period, which is 2 pi over k. We know everything here, so let's plug in. B is 1/3, so we have 1/3 comma 1/3 again plus the period, which is 2. All right, this period. So this period right here is 2. Okay. So we have plus 2. Therefore, the interval over which this function completes one full cycle is, take the common denominator there, you get 3 times 2, 6 plus 1, we have 7/3, right? That's the interval over which the function completes one full cycle. So what else do we need to graph this? Do you remember? What else do we need? Because cosecant function, or right here, the cosecant function is the reciprocal of, let me quickly use my scratch paper here. Because the cosecant, general cosecant function, is the reciprocal of the sine function. So wherever the sine function is equal to 0, we're going to have a vertical asymptote. But of course, in this case, our original function was not x, it was this whole thing. So let's find, so if this argument is 0, then this whole thing becomes 0, and this cosecant becomes undefined, right? Because if sine function is 0, then this is undefined, and we don't want that. So we need to find all the vertical, or a few, not all, but a few vertical asymptotes, so we know where the graph should go. So in this case, the inside, let's make sure that we find where this thing is 0, because we don't want our graph to cross that point, right? So we're looking for x. Whatever x value that would make this quantity equal to 0, we need to find it. So let's set this expression equal to 0. So let me go to the other page. So we have, so finding, I'll just say finding a few vertical asymptotes, right? We don't want to find all of them, just a few. Asymptotes, so we have, let's set that expression equal to 0. So this is pi x minus pi over 3, right? Equal to 0. Let's solve for x. So we have pi x equals pi over 3. Let's divide both sides by pi, or multiply both sides by 1 over pi. So what do we get? We get x equals, so I don't know, maybe I should have just shown that, but it's okay. So we're multiplying both sides by 1 over pi. and we're going to get x equals 1/3. So that's one of the asymptotes. Okay, let's find a few more. How do we find a few more? Well, see, let me find my the other page here. So we know that this is our interval, right, over which the function completes one full circle. And so the cosecant function is symmetric. Once we draw it, you'll see, you've seen this before, the curves are symmetric. So halfway, if 1/3, or the beginning of this interval is a vertical asymptote, then I should actually, let me modify this interval by doing this, right? Since we just discovered that 1/3 is an asymptote, so I'm just going to put a parenthesis rather than bracket because the function is not going to go through there. So parentheses excludes it there from that. So then this interval is 2 units in length, right? 7/3 minus 1/3 would be 6/3, and 6/3 is 2. So half of that, take this interval and halve it, and take the half of that. 2 divided by 2 is 1, right? So that 1 unit added to 1/3 gives us what the other asymptote should be. Okay, so let me, many of you, if not all of you, can do this in your head, but let me just show it on paper, okay? Just for the sake that in case somebody has questions, they can look up the notes and have that. So we have another asymptote, so let's then, so 7/3 minus 1/3, this will be 6/3 equals 2. And this is the length of the interval over which the function completes one cycle. So let's take the half of that. So 2 divided by 2 is going to be where the other asymptote is going to be. So 1 unit, 1 unit to the right of 1/3. So let's find that. So then we have, so once we know one asymptote, we can calculate the other ones easily around it. We can subtract 1 from this to find asymptotes to the left. We can add 1 to this to find the asymptote to the right. So therefore, so other, I'm just going to say other vertical asymptotes occur at, here are a few more. That is in addition to this, right? We have x equals 1/3 plus 1. Take the common denominator, you're going to get 4/3, right? So that's another asymptote. Let's find another one. Let's subtract. So this is one asymptote to the right of this. Let's find the one to the left. So 1/3 minus 1. So we have minus, take the common denominator, we have minus 2/3. Let's find another one to the right of this one. So what does that mean? How can we do that? So add 1 to this. Okay, so 4/3 plus 1 is going to give us another asymptote. So let's take the common denominator, and this would be So 4, and we have 7/3, right? That's another asymptote. Let's find another asymptote to the left of this. How do we find that? Subtract 1 from this, right? How did we get this? We subtracted 1 from 1/3 to find the next one to the left. The next asymptote to the left, we subtract 1 from this. So let's do that. Minus 2/3 minus 1 would be equal to, so we have minus 6, minus 2, and minus 1, minus 3, so we get minus 5/3. Okay? So I think these plus this one, these 5 asymptotes are plenty for us to graph this function. And I have a little bit space left on this page, but I don't think it's enough for me to do a good graph on this portion of the page. So let me go to the next page, and we'll use all of that to draw our graph. Okay, so we have something maybe here somewhere. I can put my x-axis. And let's put the y-axis right there. Right, like that. Yeah, that pretty much fills this screen. So let's do, I guess, up to 3. I don't want to make this drawing too crowded, so I'll just do 1, 2, and 3. Yeah, that should be enough. And then 1, 2, and 3. So negative 1, negative 2, negative 3, 1, 2, and 3. The amplitude is 2, so we want at least 2 increments here. Let me do that. So we do 1 and then 2. That should be enough. Right? Like this. 2. And then we should have 2 units on this side. Maybe here, minus 1 and minus 2. Like that. Okay, so let's plot these asymptotes. 1/3, minus 2/3, 4/3, minus 5/3, and 7/3. Okay, so this was the other one. So if this is 1, then 1/3 would be somewhere here, let's say, right, roughly. So we have this would be, let me stop there and say this is x equals 1/3. Then the other asymptote that we had was positive 1. Let's plot the positive ones first. So 4/3 and 7/3, right? Let's get those done. And so we have 4/3. 4/3 would be a little bit over 1, so I'm just going to put it here somewhere. Maybe here, that would be better. All right, so this would be x equals 4/3, and we had another one at 7/3, right? 7 positive 1. So 7/3 would be a little bit over, or 1/3 plus 2. So let's put that here. these asymptotes should be equally distant from each other. I don't know if I'm doing a great job of that, but they should be equally distant from each other, even though I cannot produce that manually. Please assume that they're equally. So this distance should be equal to that distance, but obviously it's not. I'm a little bit off. But this should be x equals, what was it, 7/3. Okay, so on the negative side also we had some asymptotes. We had one that was minus 2/3, right there, and then minus 5/3. So let's plot these two asymptotes. Minus 2/3 is a little bit on this side of minus 1, right, somewhere there. Again, I'm trying my best to keep these equally distant from each other. So this would be x equals minus 2/3. Then another one at minus 5/3. And that would be somewhere right before, a little bit before negative 2. So let's put that here. Like that. So x equals minus 5/3. Oops, I just noticed I was off the screen at the bottom, so let me raise this up a little bit like that. Okay, so now the amplitude is very important. It's 2, so we can't, I'll have to scroll up and down, guys, because my graph is a little bit, or I can maybe zoom out. Let me do that. Let me zoom out. So zooming out. Okay, that's better. Yeah, this is better. So that way I don't have to zoom or scroll up and down. So let's also put some dashed line through the 2's, 2 and negative 2, to make sure that we our amplitude is correct, right? Like that. And also here, 1 through negative 2, like that. Okay, so now we can easily graph this function. We have, let me make sure that I have that. Okay, so one piece of this graph, it's going to go between these. I should continue these asymptotes like that, like that, that, and like that. Okay, so we have one piece of this, that graph that will go like this. Okay, it's staying above, so the amplitude is 2 right there, so everything goes from 2 to positive infinity. Then we're going to have another, I guess I can move this up a little bit. So now I have to stay on this side, so we have another piece that does that, like that. It shouldn't touch the asymptote, so let me put the line like that, like that. And this goes through like that. And then we will have, these will alternate, right? So if we have one here, we skip this, and then we have another one here. So they alternate. On each side, these they should alternate. So that will be blank, and then that one goes there. So we have one there. We can't have one here. Then we have one on this side. We have one there, one piece there. So we cannot have one here. Instead, we should have one here between 4/3 and 7/3. So let's draw that like that. So like this. and like that. Okay, so that should do it. Like that. So this is basically the graph of that original function. And let me, I guess I can write the function right next to it. Right here, y equals 2 cosecant of pi x minus pi over 3. Okay, we just graphed that. Okay, I want to thank you for watching this video, and I hope it was useful. And thank you to any of you who contributed to making this video an improved one. And for now, have a nice day, and I'll see you again next time.